Welcome. In today's video, we are going to derive the maximum likelihood estimates for the negative binomial distribution. In particular, we are going to derive the maximum likelihood estimate for the value of P, the success probability in each experiment, where the value of R, in other words, the number of successes until the experiment is stopped, is known. So to begin with, let us first define our problem, and we do it in such. Suppose we have a sequence of random variables, x1, x2, all the way up to xn, and let's say they are independently and identically distributed with a negative binomial distribution with parameters R and P. Then the PMF, the probability mass function of xi, is given by the following. And I'll write P subscript x of xi, given our parameters R and P, is given by xi plus R minus 1 xi, so choose xi, 1 minus p to the power of xi, p to the r. And we know that this is true for xi, an element of 0, 1, 2, and so forth. So the likelihood function, which is ln, of the parameters R and P given a set of data x bar. Notice here just x vector is the vector of data points x2 dot 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 all the way to xn. That likelihood function is given by the respective product of all the PMFs. So I'm just going to write that down here, RP. We can then do some simplification here, or not simplification, but perhaps more some substitution. That's I equals 1 to n, and let me take a copy of this particular function here, copy and paste that there. It's the product of those functions there. Then, of course, what we're going to do is we're just going to expand this, this product here, noting that we can take the product of the first terms, so xi plus r minus 1 xi. So we take the product of the first, and I'll actually put brackets around that so it's a little bit more clear in the first instance. Then we can multiply by the product of the next terms, which is 1 minus p to the xi. And then finally, we've got I equals 1 to n of p to the r in the very final component. Now, not much simplification we can do right now in terms of the first term, so I'm actually just going to take the first term, copy that down, and leave it as is. For the second term that we have here, I'm going to sort of expand it so that we have a clearer picture. We could expand this out to 1 minus p to the x1 times 1 minus p to the x2 times dot 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 times 1 minus p to the xn, which isn't too bad for this particular problem here, or for that particular expansion. And then the last term here, although there is no dependency on the index here I note that we still have a product from I equals 1 to n, and that actually means that we need to multiply that p to the r by itself n times, if you want to think about it like that. So then after a little bit more simplification here, We've got, again, the term at the front doesn't really change, so I'm going to copy that down and leave it as is. With the second term in the sequence, I noticed that we can actually use one of the power laws here. So in this particular instance, we've all got the same base of 1 minus p. And because we have the same base, 1 minus p, 1 minus p, it means we can add all the powers together. In other words, x1 plus x2 plus all the way to xn. Or, in some shorthand notation, we can just write the sum of I equals 1 to n of xi in the power, which is a little bit of a nice succinct expression there. And then, of course, we have our p to the r's. We're multiplying those by n times. So in some sense, we can just rewrite that as p to the rn. Because again, we can think of our power laws. We've got r plus r plus r plus r plus r n times. So we have rn in total in that power. And there you have it. We have the first component, which is the likelihood function. All right, now that we've got that, let's move on to the log likelihood function. And recall that the log likelihood function, which I will write as Rp given our data, our vector of data, is by definition equal to log of the likelihood function. And then I'm going to take log of, I'm going to take this expression here, which was our likelihood function. I'm going to copy that down and I'm going to paste it here. And I'm just going to put that in brackets. Now, first component to recognize is when you have a log of a product of terms. See, we've got product. We can sort of think of this as a product of multiple terms here. That is the equivalent of the sum of their individual logs. So that one becomes log of the first component, I equals 1 to n of xi plus r minus 1 xi. So it's log of the first component plus log of the second component, which is 1 minus p to the power of I equals 1 to n of xi. Finally, plus log of p to the rn. Now, I'm going to do a little bit of a not tricky, but sort of a simplification. I'm going to try and do it in 2 steps here. Notice again, we still have a log of a product of terms. Now remember, we know that log of a product of terms is going to be equal to the sum, so I equals 1 to n, of log of each of the terms inside the product, the original product. So we can rewrite this first expression as the sum of logs. Logs of a product is sum of logs, in some sense. With the second term, what we're going to notice is, remember, using our log laws, we've got a power log of something to a power, which means we can actually bring the power to the front of the log. So we can rewrite this as, well, actually I'm going to rewrite it as 1 minus p sum of I equals 1 to n of xi. And then finally, we're going to do something similar here. With our r to the n, we've got p to the rn. We can bring the rn out the front. And that's exactly what we'll do. We've got rn log p. And there we have it. We have our log likelihood function. So now I'm going to take a copy of that and bring it to the next page so that we can do a bit more analysis on this one. So again, we have ln of our p given our data is equal to that. Now again, to derive the maximum likelihood estimate, remember we're trying to find the maximum likelihood estimate of p, we're going to have to differentiate this function, or partially differentiate this function with respect to p. So let's do that now. The partial derivative of r of our log likelihood function with respect to p, well, let's have a look. The first term that we see here is not dependent on p, so actually collapses to 0, so we can ignore that term altogether. This component does depend on p, but it's actually just this component which depends on p. So if we were to remember to differentiate a log, what we need to do is we need to take the derivative of the inner function, which in this particular case is just -1. So negative. And then we have 1 over the function itself. So that becomes 1 over 1 minus p. And then it becomes sum of I equals 1 to n of xi. And we've done that first one. And then similarly here, what we have is another component which depends on log p. And in this another component which is log p, and we know that the derivative of log with respect to p is just 1 over p. So then we can rewrite this expression as Rn over p, which is quite useful. And if I wanted to, and what I might do just for the next part of this, is I'm going to rewrite it as -1 minus p to the -1 times I equals 1. In fact, before I do that, what I might do is I'm going to just note here that I'm going to define a new term just on the side here in yellow, or maybe in green, and I'm going to define this new term xn bar, which I'm going to define as 1 over n I equals 1 to n xi. In other words, I'm going to define x bar n as the sample mean of a series of data points, in particular where you have n data points. Sometimes you might just see this as x bar, but I'm just going to put that subscript n to denote that there are n data points for clarity. Which actually means that if we rewrite this particular function here, we can rewrite, or we can redistribute the n, which means n multiplied by the sample mean is actually going to get you back to the sum of all the data points in your data set. So, keeping this in mind, I'm now going to rewrite our sum of I equals 1 to n simply as n xn bar. And that's just for added simplification. And I guess in some sense it's now expressing the log likely, or the derivative of the log likelihood function in terms of a statistic of the distribution, right? The sample mean. And then in this particular case, we've still got our right. Going back to what I was originally doing, where I was trying to express all our fractions in terms of negative powers, then we'll have Rnp to the -1 to finish that off. So keeping that in mind, we're now going to take the second derivative of this function and with respect to p, and this is going to give us the following. So It's a bit of a doozy, this one, but let's try and work this out. We've still got our negative at the front, -1 at the front from this negative. Then what we need to do when we take the derivative with respect to this particular parameter, the first thing is to note we need to take the power down the front. So then we're actually going to multiply by -1. But the other component that we need to be aware of is we need to take the derivative of the inner function, which is -1, and bring that to the front as well. So then that becomes -1, and then we've got 1 minus p, and then we take 1 off the power, which gives you -2. So a bit of a complicated, convoluted way. You can see how it could get a little bit tricky with all your negatives there. Hence why I wanted to be very clear in the first step above expressing it in negative powers. The next step, I guess, of course, is to differentiate this one, and this one's not as bad, because again, we just take the -1, bring it down the front, so it becomes minus, and then we've got Rn and then p to the -2 once you've taken 1 off the power. And apologies, before I get carried away with myself, we still, of course, have the nx bar n in this term here. So, once we've established that, we can now sort of express things in a little bit more nicer terms. This becomes minus, once you multiply 3 -1s with each other, becomes minus nx bar n all over 1 minus p squared minus rn over p squared. And there you have it as your second derivative. Now that we've all established that, we need to actually solve for the maximum likelihood estimate. And to do that, note that, again, it's a known value of r, so we don't have a maximum likelihood estimate of r in this particular example. So the first derivative of the log likelihood function evaluated at p equals p hat is equal to 0 by definition of how we derive the maximum likelihood estimate. This means that going back here, going back to this particular expression, paste that in there, the sum of so and so is equal to 0. This then, putting p hats, of course, now in our first derivative of the log likelihood function. Then this means let's do some rearranging. And to do the rearranging here, what ideally I want to do is get all our p hats on one side. In this particular scenario, the best course of action is probably to first take the -1 on 1 minus p hat onto the other side. So that's what I'm going to do. That gives us Rn on p hat is equal to the sum of I equals 1 to n of xi's all over 1 minus p hat. So after some rearranging, what we can do is we can take our r and our n to this side and our 1 minus p to that side. That way we isolate the 1 minus p. So we've got 1 minus p hat all over p hat is equal to the sum of I equals 1 to n of xi over Rn. Then if and only if notice that this expression here we can rewrite as 1 over p hat for the first component, and then for the second component that collapses to minus 1. Now on this side of things, we note that if you've got the sum of xi's from I equals 1 to n and you divide by n, this by definition is the sample mean that we defined above, and then we're still dividing by r. Finally, well, second last step, we can add 1 to both sides. So if we add 1 to both sides, we get 1 over p hat is equal to xn bar plus r all over r, which is quite nice. And then finally, if we take the reciprocal of both sides, this means p hat is equal to r over r plus xn bar. And finally, we've come up with a solution, or a maximum likelihood estimate. Now, the final step is to also show that this is, in fact, a local maximum. And to show that it is a local maximum, we need to use the second derivative test. Just noticing, though, that the second derivative of ln of r p given the vector over the second derivative with respect to p is equal to, now we had it above, here it is, copy that down, and if we don't, we notice that. Now, I'm actually going to take the negative out as the common factor, and now you'll notice that if we do take that negative out as a common factor, this term is always going to be greater than 0. This term is always going to be greater than 0. So together they're always going to be greater than 0, which means negative of something that's greater than 0 is always going to be less than 0 for all values of p in 0 to 1 in our possible range of p values. And so then this therefore implies in our final step that our p hat is in fact equal to r on r plus x bar n, and I've just written it as a statistics of random variables here. So